All right, welcome everyone to the E3SM All Hands webinar. Today we have Matt Hoffman, and have you been at the lab for what, 10 or 12 years?
Yeah, about 12 years.
Okay, great. And he's one of the original developers of MPass Albany land ice, and he's busy this year with both an early career award and the lead of the SIDAC, which he'll be telling you about now.
All right. Thank you, Mark. And thanks to Mark, Jill, and Wu Yin for the invitation to present this overview of the SIDAC project. The name of our project is Framework for Antarctic System Science in E3SM, and it's a large collaboration with 4 national labs and 3 universities, and it's co-led by myself and Mauro Perego at Sandia National Labs. And we have a very large team, and this is in part because we're building off of a couple previous SIDAC ice sheet modeling efforts. So we have a team that's worked together efficiently for a long time and has grown over the years. I've noted here people who are part of the SIDAC Institutes, both Fast Math and Rapids 2, and our team members who are also on the E3SM project. Okay, and I'd also like to thank BER and Oscar for supporting this work. So I'll just give a brief motivation about why we're focusing on the Antarctic. The Antarctic ice sheet is the largest uncertainty in future sea level change. So historically, the Antarctic contribution to global mean sea level change has been very small relative to the others. However, future projections vary widely for what will happen to Antarctica due to a number of different factors. And this schematic that we've prepared here on the right shows in this blue color kind of the uncertainty associated with the basic known physics of ice sheet dynamics and marine ice sheet instability. Whereas there's additional concerns about ice shelf basal melting, and that is very poorly constrained, and the potential for hydrofracture of ice shelves, which I'll talk about a bit later on, that raises uncertainty quite a bit. And then there's also this concept of marine ice cliff instability having to do with the fracture of ice cliffs in the ocean and positive feedback that can ensue there, and that has much deeper uncertainty. So even by 2100, we're looking at anywhere from close to a meter of sea level rise to a sea level fall contribution from Antarctica. So this is the biggest uncertainty to get a handle on for future projections of sea level. And as I just alluded to, the reason this is because of feedbacks and tipping points in the Antarctic ice sheet system, as well as coupling and interactions with the climate system, both the atmosphere and surface climate, as well as the ocean. And so I just mentioned these 4 sort of key processes briefly, but to elaborate a bit more, the concept of marine ice sheet instability has to do with the flux of ice from the grounded region of the ice sheet into the ocean is proportional to the ice thickness at the grounding line, or the position that the ice goes afloat. And when the ice sits in an over deepening like this, a slight forced retreat of the grounding line leads to a thicker ice sheet at this transition location and a larger flux. And that larger flux draws down the ice sheet and leads to potentially runaway retreat in this geometric configuration. The marine ice cliff instability is similar in that when you have a subaerial cliff at the terminus in a marine location, there's above a certain thickness of the ice above the waterline, the ice becomes unstable and will crumble and collapse, and that will lead to a thicker cliff and potentially a positive feedback. And this instability is very poorly understood. Somewhat similar to that is the concept of ice shelf hydrofracture, where you have these ice shelves which buttress or restrain the flow of the grounded ice behind them, even though the ice shelves themselves don't directly contribute to sea level change. And the ponding of surface melt can fill crevasses and lead to the expansion and growth of collapses and potential catastrophic collapse of entire ice shelves. And so that's an atmospheric driven interaction. And then finally, we have the potential for a regime shift in the ocean driven melting beneath ice shelves and at grounded marine termini, where warm ice shelves, or sorry, cold ocean water cavities can switch to a warm water mass mode if warm water masses such as circumpolar deep water intrude underneath the ice shelf cavities. So this is the wide array of processes that we really need to capture to realistically project what's going to happen to Antarctica. And while previous SIDAC projects and ice sheet modeling efforts in general have really advanced the state of ice sheet modeling to improve ice sheet dynamics, these interactions and physical processes are poorly represented in pretty much all ice sheet models right now, let alone climate models. So to address these main topics, we've divided the FANCY project into these three focus areas. The first is advancing and completing the coupling between the Antarctic ice sheet and the climate system within E3SM. The second is further improvements to ice sheet dynamics and fracture mechanics. And that also includes advancing numerical methods and improving performance of the MAHLI ice sheet model component. And then finally, these two activities kind of unite in producing probabilistic projections of the Antarctic ice sheet within the E3SM ecosystem. And so the overall science question we're tackling, as I've kind of motivated so far, is how will these threshold processes that link the coupled ice sheet, ocean, and atmosphere impact the contribution of the Antarctic ice sheet to sea level change in the coming decades and centuries. Okay, so I'll go through kind of the plans for each of these areas, as well as how much progress we've made so far. We're about 1 year into the project. So the first main area is the coupling of the Antarctic ice sheet to E3SM, focusing on ocean interactions. And the problem here is that many MPAS Ocean and E3SM, like many climate models, until recently did not have even the representation of ice shelf cavities. In E3SM version 1, MPAS Ocean was expanded to support the circulation of the ocean beneath ice shelves and the prognostic calculation of ice shelf basal melt rates, which is fundamental for driving ice sheet evolution. However, the extent of these ice shelf cavities is currently fixed in MPAS Ocean, and that prevents dynamic coupling between the ice sheet and ocean. And so as the ice sheet evolves, the ocean domain must advance, which is a major technical hurdle. And this little animation just shows an extreme case of, the sorts of grounding line retreat or ocean advance that might be necessary in the future. And so the goals here are to add these developments to MPAS Ocean to support the growth of the ocean domain. And we're doing this through adding regions of the mesh that are initially inactive but can become activated through the presence of a thin film in the ocean model. And then additionally, to support that, we're improving the vertical coordinate to avoid steeply sloping layers and introducing a higher order pressure gradient calculation. And this is work that's primarily been led by Carolyn Begeman and Tyler A.C. Davis here at LANL. And the progress so far has been really fantastic. This is a tough problem that was started under the previous SIDAC project Prospect. And in the last year, Carolyn has demonstrated a operational capability of this thin film wetting and drying. So here's just a simple test case showing ice sheet in red and ice shelf cavity here. And after 1 month of imposed ice shelf thinning, this grounding line has retreated and the ocean domain has expanded to fill that space. So we're currently kind of working on verification and some additional improvements of this capability, but it is up and running. And just as an aside, I want to mention we are looking at some potential challenges with the E3SM transition to Omega because we're invested in completing these capabilities in MPAS Ocean. And that's because ice sheet ocean coupling requires ocean model features that are not typical or standard for global ocean models. And while Prospect and Fancy have been significant investments in these areas for MPAS Ocean, additional work will be needed to bring these capabilities into the new Omega model as that comes online. And specifically, the existence of ice shelf cavities in the ocean model, as I already said, is fairly novel. The wetting and drying, or the motion of the grounding line in the ocean, is an even harder problem. And then we're also stuck with the issue that in polar regions, eddies are very, very small. And so even at ultra high resolution, they will not be fully resolved in the polar regions, and that necessitates a more sophisticated eddy parameterization than Omega is currently planning initially. So we are coordinating with the Omega and E3SM polar teams, but this is just kind of a heads up to the larger community that there will be some challenges in maintaining these capabilities we're developing in E3SM as E3SM changes ocean models. Okay, so with that aside, one other aspect related to the ice sheet ocean interactions that we're adding is the addition of subglacial discharge from the ice sheet to the ocean, which has a known important effect on the ice shelf cavity circulation. And it's been demonstrated to be very important for Greenland, but has received little attention in Antarctica. So we've been using Molly's subglacial hydrology modeling capability to generate these maps of subglacial discharge into the ocean, and we're working towards adding that flux through the coupler and into E3SM and MPAS Ocean. Okay, so moving on to the second area of coupling to climate with the Antarctic ice sheet is the surface climate. And I already motivated how ice shelf hydrofracture can occur when the snow and firn on the ice sheet surface or the ice shelf surface become saturated with meltwater and can drive fracture completely through the ice, as shown in this set of photographs here. So our goals in this area are to improve and validate the snow and firn physics in ELM, and then eventually connect firn water content modeled in ELM to the ice shelf stress state modeled in Molly, so that we can prognostically model ice shelf hydrofracture. This is work led by Charlie Zender's group at UC Irvine. And our progress so far in this area has really been getting the baseline snow and firn physics and Antarctic surface mass balance improved, because until those capabilities are realistic, we can't hope to tackle these more complicated aspects. And so progress so far has been, Charlie's group has evaluated 5 different global atmospheric reanalysis products against both Antarctic and Greenland firn core records, and identified that ERA 5 was the best and most accurate reanalysis product to use for ice sheets, and through that has added ERA 5 as a data atmosphere option in E3SM, which is, I think, has benefits far beyond our project. And then on using that new reanalysis atmospheric forcing, they've completed a 300-year firn spin-up, because the firn has a very long equilibration timescale of hundreds of years. Using this reanalysis forcing to produce Antarctic ice sheet surface mass balance coming directly from E3SM that has spatial pattern and magnitude that's very similar to reanalysis and other climate model reference values. So this is looking very exciting that we have a credible surface mass balance for both Antarctica and Greenland through Charlie's group's efforts. So I'm going to move on to the second phase of FANCY, which is really focused on developments within ice sheet model physics and performance. And I'm going to start with the part of MOLI that's improving the discretizations and numerical methods used in the model. So historically, as Mark said, MOLI's been in development about 10 years, and the initial version of MOLI implemented primarily first order accurate numerical methods, but we really need higher accuracy at reduced costs to represent the complicated behavior of ice shelf fracturing and other dynamics. So we're replacing these more simple algorithms with higher order discretizations. And at the same time, we're also pursuing some lower fidelity model options for cost savings where that's appropriate. So progress there is Mauro recently has implemented a depth integrated velocity solver as an alternative to our more expensive three-dimensional velocity solver, and demonstrated that it has similar accuracy at 3 times cheaper computational cost. And that's particularly important because the velocity solver is about 90% of the total cost of an ice sheet model. So making the velocity solver cheaper cheapens the whole model by quite a bit. In other areas, Trevor Hillebrand has been leading an effort to implement higher order advection and time stepping. So he's replaced our first order upwind advection with third order flex corrected transport scheme that MPass Ocean uses. And he's replaced our forward order time stepping with a third order strong stability preserving Runge-Kutta method. And you can see with our old system, what I'm showing in these pictures is ice shelf damage. And with the first order methods, everything just looks very smooth and diffuse, as you might expect. But with the third order methods, we're really resolving sharp features, which are critical for predicting ice shelf behavior. And then finally, here's just a picture showing improvements in our initialization capabilities. So often the most computationally intensive and difficult aspect of ice sheet modeling is initializing the model, because ice sheet models have a memory of thousands to tens of thousands of years. The initial state is incredibly important to your projections. And this is an example of initializing the ice sheet both velocity and temperature simultaneously, done by Mauro. And importantly, he's shown a fantastic improvement in the number of linear solves required to converge this inverse problem by improving the preconditioning and other aspects of the inverse model. Okay, so I'm kind of transitioning from these discretizations into ice shelf fracture mechanics. So existing fracture models, like the one we currently use in MOLI, just use simple stress or strain-based parameterizations to parameterize the calving of icebergs at the ice shelf margin, where in reality, as you can see from this satellite image of the Thwaites ice shelf here, with ice flow shown by this blue arrow, and the transition from grounded ice to floating ice shown by this red line, is that the ice shelf is highly fractured. There's channels, there's weak zones, there's shear margins, there's all sorts of complex behavior that just is not really resolved in our simple von Mises stress criterion that we're currently using. So our goals here are twofold. The first initial approach is to introduce a damage state variable into the ice sheet model that evolves based on both the stress state and the surface and basal melt forcing that ice shelf experiences. and that can lead to the calving of failed ice when damage exceeds some threshold, but also can feed back into ice sheet dynamics by weakening the ice viscosity. And here is an animation that Trevor Hillebrand produced using the higher order advection and time stepping that I described previously to show how ice shelf damage is really evolving in a realistic way that has much more of the complexity that you see here, and that these sharp features are maintained in time. And you can see there's points along the grounding line that are high stress concentrations, and high damage is just sort of radiating out from them. So we're getting much more realistic behavior. And for context, most ice shelf or ice sheet models that are used for whole ice sheet projections until now have just been assuming a fixed calving front position of the ice shelves. And so this is a very much more realistic approach. Okay, and then longer term, we also want to introduce ductile and brittle methods, so a hybrid rheology for ice that allows the formation of rifts and tabular icebergs, because calving through tabular icebergs is the primary way in which Antarctic ice shelves produce icebergs. So here's just an example of a prototype model by Jeremy Bassis at the University of Michigan that is breaking off these intact tabular icebergs instead of just assuming some sort of calving flux falls off the end of the ice shelf. Okay, so to support these advanced fracture problems, especially the formation of rifts and tabular icebergs, we're also introducing unstructured mesh adaptivity using level sets and a mesh adaptivity library developed through FastMath at Rensselaer Polytechnic Institute called Omega H. And Omega H is GPU based, which allows us to utilize current DOE computing architectures. And this allows our triangular mesh to adapt and move with some discrete feature that we track with a level set. So this is just a proof of concept showing how we can modify the mesh using Omega H to follow these features, and that should allow for much more accurate solutions at calving fronts and rifts as we introduce that capability. Okay, so we've also been working towards performance improvements with Molly, and as I alluded to, a lot of these new physics will impact the performance because they're going to be more computationally intensive. So we've been working on algorithmic improvements to better utilize GPUs, including new preconditioners that are specific to GPUs, and working on load balancing and auto tuning, as well as software modernization and moving parts of the code from Fortran to C++ to take advantage of the Cocos library that allows us to be more performance portable. And this is just a scaling plot prepared by Jerry Watkins at Sandia, showing that we are utilizing GPUs effectively for a non-local PDE type problem. We're doing quite well, and that Molly is scaling up to hundreds of millions of unknowns on GPUs. And just a few months ago, we had our first Antarctic ice sheet production runs using GPUs. And as far as we know, we're the first kind of large-scale ice sheet model to demonstrate that capability, which is very exciting. Okay, so that kind of brings me to the final phase of the project, which is combining these different developments to actually enable probabilistic projections of the future of the Antarctic ice sheet. And this is going to really require improvements to uncertainty quantification and the implementation of large ensembles of Molly simulations. So progress so far, kind of our baseline capability is, here's some examples of whole ice sheet simulations we've done this year, which is Molly's and DOE's contribution to the International Ice Sheet Model Intercomparison Project, projecting the Antarctic ice sheet out to 2300. Here's just an example from one simulation with our 4-kilometer regionally refined mesh of the ice sheet at the initial and final times. And in this case, we've done about 15 different scenarios and a number of sensitivity tests just to kind of get a baseline understanding of model behavior. And you can see very clearly that under low greenhouse gas emission scenarios, there's very modest sea level contribution from Antarctica, and under high greenhouse gas emission scenarios, potentially more than 2 meters by 2300. And this is consistent with other models in this inner comparison. But this is not really uncertainty quantification. So what we're moving towards is running large ensembles of MOLI along with emulation and Bayesian calibration to create probabilistic projections. And this is our current project is using just the Amory ice shelf sector of Antarctica, shown here in light blue. And we've run a 200-member, 6-parameter ensemble of 6 of the most uncertain MOLI parameters. And we're using a Gaussian process emulator in order to produce the tens of thousands of samples necessary to perform Bayesian inference and generate posterior distributions for these uncertain parameters, and then project those forward out to eventually 2300 to generate PDFs of potential sea level contribution from this sector. And this project is nearing completion, and then next year we will transition to applying these methods at the whole ice sheet scale. And then finally, the ultimate goal is to be, by the end of the project, performing E3SM simulations with the fully coupled Antarctic ice sheet component that resolves all these key processes I mentioned at the beginning. And even when we're doing that, it will not be possible to run large ensembles of E3SM, we expect. So we also want to be able to run ensembles of standalone MOLI, but forced by ocean and atmosphere climate forcing derived from these fully coupled E3SM simulations. And so we've designed a workflow that will allow us to kind of produce ice shelf basal melt maps for a given thermal forcing that we can introduce into these ensembles. And this sort of activity will come later in the project. So that's where we're headed. And I'll just stop here with a summary. And again, the 3 main areas of the project are coupling of MOLI to E3SM, improvements in MOLI ice sheet dynamics, and with a focus on fracture mechanics, and then these probabilistic projections of the future of Antarctica. And we've been working closely with E3SM project and other ecosystem projects, as I've alluded to, and we're hoping that this SciDoc project helps maintain DOE leadership in ice sheet science and development. So thank you for your attention, and I will stop here.